Why has the sky over the North Atlantic seemed to stall this summer, parking the same weather patterns in place for weeks instead of cycling through the way it normally does? That question sent researchers looking somewhere nobody would expect to find the answer, not in the atmosphere at all, but in the ocean current running silently beneath it. The investigation starts with what's actually visible from the surface. Meteorologists across Europe have spent this summer describing an atmosphere that keeps getting stuck, high-pressure systems rebuilding in the same place faster than expected, jet stream patterns buckling into unusually persistent loops, heat wave after heat wave, settling over the same regions instead of moving through, giving way to normal variability. That's the surface-level mystery. But the atmosphere and ocean aren't separate systems. They're locked together, and investigators studying the North Atlantic specifically went looking at what the water underneath has been doing, because a stalled sky sitting above a stalled current would be far more than coincidence. That instinct to look beneath the surface rather than only at the sky itself comes from a basic principle oceanographers and meteorologists have understood for decades. The ocean stores and releases heat far more slowly than the atmosphere, which means its currents act almost like a memory system, holding on to patterns for years or decades at a time, rather than shifting week to week the way weather does. If something fundamental is changing in that slower, deeper system, the atmosphere sitting above it doesn't necessarily change overnight. It changes gradually, showing up first as subtle shifts in how long weather patterns persist, before finally investigators find the underlying mechanical cause months or years later. That search led directly to the Atlantic Meridional Overturning Circulation, known as the AMOC, a vast system of ocean currents that functions as a conveyor belt, carrying warm, salty water north from the tropics along the surface and sending colder water back south along the ocean floor. This isn't a minor regional current. It's one of the most powerful drivers of heat distribution on our entire planet, and it's the specific reason Northern Europe runs several degrees warmer than its latitude would otherwise suggest. Investigators pulled the most direct evidence available first. Actual measurements, not models. A research team from the University of Miami's Rosenstiel School analyzed nearly 2 decades of data from 4 separate ocean monitoring arrays stretching along the western boundary of the North Atlantic, from the tropics up to higher latitudes. Using seafloor-anchored instruments continuously recording pressure, temperature, density, and current speed, they found a consistent weakening trend at every single one of the 4 locations. That consistency across such a wide geographic spread is exactly what convinced the research team this wasn't a temporary blip or regional fluke. It reflected something happening to the entire large-scale system. Here's how the lead scientists on that team explained why finding weakening at all 4 sites mattered so much. Physical oceanographer Shane Elipott described the western boundary measurements as a kind of early warning system, a canary in a coal mine, for the broader AMOC. When a signal shows up consistently across multiple independent monitoring points spanning thousands of miles, investigators treat it very differently than a single anomalous reading because natural year-to-year variability tends not to produce the same trend everywhere at once. Real observational data, confirming what climate models had already been predicting, is precisely the kind of convergent evidence that shifts a hypothesis into something closer to an established finding. Like and subscribe if you want investigations like this one, tracing a strange atmospheric pattern all the way down to its actual physical cause, because that's exactly the kind of connection headlines usually skip over. With the observational evidence established, investigators turn next to what the projections actually say about where this trend is heading, and this is where the findings started escalating. A separate study, published in the journal Science Advances, ocean temperature and salinity data to map out the AMOC's likely future. The team found that most existing climate models have been underestimating the decline. Their revised projection put the AMOC on course to slow by more than 50% by the end of the century, under a mid-range emission scenario, a reduction roughly 60% steeper than the average of previous model estimates, which had generally clustered around a 32% slowdown. That gap between old projections and new ones is worth sitting with. It's not just that scientists confirmed a slowdown was happening, it's that when they went back and checked their own models against real measured data, the models turned out to have been too optimistic, understating how fast the system is actually weakening. Investigators tracing this thread found a specific culprit driving that model correction: meltwater. As Arctic and Greenland ice melts, it dumps large volumes of cold, fresh water into exactly the region where the AMOC's northern branch normally sinks, disrupting the density-driven process that keeps the whole The mechanism itself is worth spelling out plainly because it's the physical engine driving everything else in this investigation. The AMOC exists because warm, salty water flowing north gradually cools and becomes denser as it travels, eventually growing heavy enough to sink deep beneath the surface near Greenland and Iceland, pulling more warm water north behind it in a continuous cycle. Much like a conveyor belt driven by gravity rather than a motor. Fresh water from melting ice dilutes that salinity, making the water lighter and less prone to sinking. Less sinking means a weaker pull on the warm water following behind it, and that weaker pull is precisely what investigators are measuring as a slowdown across all 4 monitoring arrays. Investigators then pulled in a third source of evidence, this one reaching back much further than either the 2-decade observational record or the forward-looking models, paleoclimate data. Scientists analyzing microscopic marine organisms and seafloor sediment layers, proxy indicators that preserve a record of past ocean conditions, found that the AMOC's current state is its weakest in more than 1,000 years. That finding matters because it rules out a simple explanation investigators had to consider and eliminate, that this is just normal decade-to-decade fluctuation the system has always experienced. A 1,000-year low doesn't fit that explanation. It fits a system undergoing a genuine, historically unprecedented shift. Now bring these 3 threads together because this is where the investigation connects back to the original question about a stalled sky. A weaker AMOC doesn't just mean colder water sitting in a different place. According to physical oceanographers studying its effects, a weakened circulation can shift weather patterns entirely, potentially producing more extreme storms, altered rainfall distribution, and in some regions, colder winters, even as the planet overall continues warming. The mechanism runs through exactly the kind of temperature gradient that drives atmospheric behavior in the first place. When the AMOC moves less warm water north, the temperature contrast between different latitudes changes, and that changed contrast is one of the very forces that shapes how storms form, how the jet stream behaves, and how long weather patterns like this summer's persistent heat domes stay parked in place before finally breaking down. It's critical to be precise here about what remains genuinely uncertain within this investigation, because the field itself is actively debated rather than fully settled. There is broad scientific consensus that the AMOC is weakening. There's real, ongoing disagreement about exactly how fast and about whether the system is approaching an actual tipping point, a threshold passed, which shutdown becomes effectively unstoppable, versus a more gradual decline that continues without ever fully collapsing. One prominent 2025 study suggested the tipping point that makes eventual shutdown inevitable could be crossed within a few decades, though the collapse itself might not fully play out for 50 to 100 years after that threshold is passed. Other researchers in the same field describe the uncertainty around timing as still too large for a reliable estimate, even while agreeing the system has been losing stability. That range of expert opinion is itself part of the investigation's honest conclusion. Physical oceanographer Neil Fraser, reflecting on how the field's thinking has shifted, noted that when the Intergovernmental Panel on Climate Change released its most recent full assessment, the consensus view held that an abrupt AMOC collapse before 2100 was unlikely, even while a general slowdown was considered very likely. Since then, several high-impact studies have specifically challenged that reassurance, arguing that an earlier assessment may have been too cautious. That's the state of the investigation as it stands right now. Strong, convergent evidence that weakening is real and already measurable, alongside a genuinely unresolved scientific debate about whether that weakening eventually crosses into full, irreversible shutdown. Danish climate scientist Peter Ditlevsen, whose analysis of sea surface temperature records stretching back to 1870 has been among the most cited work pushing the tipping point timeline earlier, has been careful to frame his own findings with appropriate caution, even while describing them as concerning. His research team's central finding was that the collapse would resemble flipping a light switch rather than a gradual dimming, an abrupt and largely irreversible shift once the threshold is actually crossed, which is precisely why investigators studying this system treat identifying the timing of that threshold as more urgent than debating the eventual outcome itself. Whether that switch flips in 30 years or 70 remains the single biggest open question in this entire field. It's worth noting how seriously governments closest to this risk are already treating it, independent of exactly where the scientific debate on timing lands. Iceland made the notable decision to formally designate the risk of an AMOC shutdown a national security threat, a striking policy move for a phenomenon that remains, by most researchers' own admission, still years or decades away from full resolution in either direction. So what does this investigation actually mean for someone experiencing this summer's stalled weather patterns firsthand, rather than reading about ocean currents in the abstract? If you live in a region prone to the kind of persistent heat domes and blocking patterns Europe has experienced repeatedly this year, Treat this as a signal worth taking seriously for long-term planning, rather than a one-off unusual summer, since a weakening AMOC is specifically linked to exactly this kind of pattern by researchers studying the connection. If you're in coastal areas of North America, be aware that AMOC weakening has been specifically tied to accelerated sea level rise along that coastline, a detail worth factoring into any long-term property or infrastructure planning in vulnerable areas. If you live in Northern Europe specifically, it's worth understanding that the counterintuitive summers, since the AMOC is precisely what keeps that region several degrees warmer than its latitude would otherwise produce. A weakening current means that moderating effect fades, potentially producing the kind of harsher, more extreme winter cold snaps that researchers have flagged as a downstream consequence, rather than a contradiction of overall global warming. And broadly, when following coverage of individual extreme weather events this year, whether a heat wave, an unusual storm, or a shift in seasonal rainfall, it's worth asking whether reporting connects that event back to this broader circulation pattern, since investigators studying the AMOC increasingly view it as a root cause, sitting underneath many of the individual weather stories making headlines separately. The sky over the North Atlantic didn't stall on its own. Investigators traced that stall down through nearly 2 decades of seafloor measurements, models that had to be revised to catch up with reality, and 1,000 years of sediment records, arriving at the same conveyor belt every single time. Whether that current eventually shuts down entirely or simply keeps weakening gradually for the rest of the century remains genuinely unresolved. What's no longer in question is that the sky and the current beneath it were never separate stories to begin with,